Alrighty, so I'm going to explain a little bit about neurotransmission and how basically neurons communicate. So looking at this picture, I know there's a lot of information, but yeah. So let's follow this website a little bit. So neurotransmission essentially begins when the neuron is at its resting potential. So at the resting potential, the neuron is basically just chilling here hanging out until it gets a signal. The way I like to see this is kind of like when you're driving, right? Say you're driving in LA and then you hit this intersection and you get a red light. Think of that as your resting potential. You're chilling, you're hanging out until you get the signal. So in the resting potential, the presynaptic neuron is at rest with a negative charge inside the neuron, and there's a positive charge outside. So we're going to talk about sodium and potassium ions. So this state of equilibrium is maintained by the sodium potassium pump. So that keeps everything kind of in balance. That keeps the neurons in balance. Think of that as the traffic signal, right? You stay on one side, cars flow through the other lane, boom. So everything is balanced. Everyone's waiting for their signal. Um, so another thing that I find really important too, or that is important, are the dendrites. So the dendrites of the presynaptic neuron, they receive this signal from other neurons, which are either excitatory or inhibitory. So those are the dendrites. They kind of look like trees or like tree branches. These are the dendrites. Um, so let's talk a little bit about excitation and inhibition. Let's see if I have a picture for excitation and inhibition. No, okay. So let's stay here. So the received signals can cause either excitation or inhibition at the dendrites. So excitatory signals trigger depolarization. So let's look at the depolarization. So right here, right? So we have the resting potential here. This is where the car is chilling. And then we have depolarization where it begins to move. And then we have repolarization. So excitatory signals trigger depolarization, whilst inhibitory signals cause hyperpolarization, right? So here we have the hyperpolarization, which is caused by inhibitory signals. And then there's a thing that we also talk about regarding graded potentials. So incoming signals cause small changes in the neurons and membrane potential. So these are known as graded potentials. These are small deviations from the resting potential. Okay, so they just deviate a little bit. And then another thing to consider is like summation. So summation occurs in two ways, spatial and temporal. So spatial summation happens when multiple signals uh, occur from different synapses. And then temporal summation is repeated signals from the same synapse over time. So that's temporal summation. So let's look at the threshold here, right? So basically you're at the red light waiting for your signal. And then once you step on the gas, you can't stop, right? If you stop your car, you're going to cause a collision. So you have to continue in your lane and continue on. So once that light turns green and you pass the threshold, say you pass the intersection, you have to continue going. Neurons have the same thing. They have this threshold. Once it passes, whoop, it goes all the way up here to the action potential, right? So we have whoop, it gets a signal, it turns green, and whoop, it begins to go up. So that's the action potential. Um, so the threshold, the summation of excitatory signals reaches a threshold at the axon hillock, where the axon begins and the action potential is triggered. Right, so let's look here. So here we have the axon terminals, and then okay, so here, the axon hillock, right? So boop, it begins to move. The information continues to move a little bit. All right, so yeah, look at here. So we have the axon, information is being sent. We have the axon hillock here, cell body here, and then dendrites. That's where all the information eventually gets sent to as well. So continuing on, one thing that is important to consider is the law of all or none. So essentially, this law means that once the threshold is reached, the neuron will fire an action potential. If not reached, no action potential occurs. Either it happens or it doesn't. So once it reaches here, the threshold, it's gonna happen. If it doesn't reach here, right below this line, it's not gonna happen, right? It either happens or it doesn't happen. Um, and let's look a little bit at depolarization. So so during the action potential, the membrane becomes depolarized. So sodium ions channels open up and sodium floods into the cell. So let's look at where it opens up a little bit. All right, so we have the resting potential here. We have potassium ions down here, sodium ions up here, right? Think of this, this is your intersection right here. So when it's depolarized, the potassium ions begin to move upward. We see that here. So the channels open up and the ions begin to shift. During the action potential travels down the length of the axon towards the axon terminals. This process is an electrical signal that moves along the neuron. Okay, so we have all these, yeah, the voltage gauge open up, the electrical signals are happening, and then eventually it gets to its hyperpolarization. So notice how it's moving here, and then it happens, and then it gets to its hyperpolarization. So after the axon potential, the membrane temporarily becomes hyperpolarized as potassium leaves the neuron, making the inside of the neuron more negative. So now the inside of the neuron is more negative, right? So it begins to shift a little bit. Um, okay. So another thing that's important is that we have what's called the absolute refractory period. And so basically the refractory period is when the neuron enters the absolute refractory period, it cannot fire another action potential. And so this is important because it ensures that the signals are going just one direction, right? So if you're driving, you have to stay in your lane. Once that signal gets fired, you stay in your lane. And so this is important for the neurons too. Like you don't want to send mixed signals, you don't want to send multiple messages. And so that's why the the absolute refractory period is important because it doesn't allow any other messages to come through until the neuron finishes its duty, so to say. Um, Another thing that's important is the sodium potassium pump. So the sodium potassium pump, it restores the original balance of the ions. And so basically it maintains balance. So here we have what we call the sodium potassium pump. Let's see if I can find another picture of the sodium potassium pump. I think the picture up here was a little nice. Okay. So essentially what the sodium potassium pump does is it keeps the balance, which is really important because you don't want to be imbalanced. Hey, but that can happen. Good. This is another really nice picture. We have the myelin sheath here. We have the nodes around V right here. And let's see. All right. So let's talk about the axon terminals. So eventually the messages reach the axon terminals. So the action potential reaches the axon terminals of the presynaptic neuron. Okay, so that's when everything eventually gets sent all the way down to the axon terminals. Let's see, we have a good picture of that right here. Axon terminals. All right, we have the terminal button right here. Boom. Good. Um, so I think I talked a little bit about this in the beginning. So we have the synapse, we have the postsynaptic neuron, and then we have the synapse. So at the axon terminals, um, the axon terminals are close to the postsynaptic neuron at the synapse. So it's a gap between the two neurons. It's where they meet. It's eventually where all the information gets sent, right? It communicates from one neuron to the next neuron, maybe communicating from one car to the next car. And so that's at the junction, so to say. So exocytosis. At the axon terminals, the axon potential triggers exocytosis, exo meaning outside, causing the release of neurotransmitters into the synapse. So that's exocytosis. Um, don't have the best pictures for that. Okay. And then ligand. So the ligand, right? Like ligament, to bind, to be bound. So the neurotransmitters act as a ligand binding to ionotropic receptors on the postsynaptic neuron. Okay, so that's where neurotransmitter act as a bind to receptors. Something that we haven't talked about yet, or that I haven't spoken about yet too much, is excitatory and inhibitory. Let's see, let's see, let's see, let's see. Okay. So I'll go to this one because this one's nice. This one's a little more thorough. I'll just stick to this picture. So looking at EPSP and IPSP. So the binding of neurotransmitters can create either an EPSP, which is an excitatory postsynaptic potential, or an IPSP, which is an inhibitory postsynaptic potential. And then all these information, they meet in the gap junction. So the gap junction allows basically electrical signals to pass directly between cells without neurotransmitters. So that happens in some cases, right? In some cases, neurons decide to communicate that way. Reuptake. So after neurotransmitters have transmitted their signal, they are either broken down or taken back up the presynaptic neuron through the reuptake, ending their action at the synapse. Alrighty. Yeah. So yeah, I believe that's essentially it. Essentially, what you need to know is that neurotransmission is the way neurons communicate. And there's a lot of information here regarding the dendrites and sending information through the axon terminals. Um, the myelin sheath actually allows the neuron signals to maintain its speed, which is really nice, right? So the neuron doesn't slow down, it maintains its speed, which is really nice. And yeah, I just think it's really incredible the way neurons communicate, and they're doing it constantly all the time. Um, yeah, it's just really, the body is just really, really incredible. Alrighty. Thanks for watching.